Good morning, class. So on Wednesday, we start to talk about independence between two events. And today, we're going to finish some discussions of this topic, and then we're going to talk about another set of very important theories. It's called the Bayes Theorem. But to start with, let me just remind everyone, what does independence mean? Independence always starts with two events, okay? Event A and event B. There is a formal definition of independence, which is that if you take the intersection of these events A and B, if you measure the probability, and if the probability can be factorized, then you say that the two events, they are independent. And that is the formal definition of independence. We will run into a lot of troubles of just applying our intuition when we think about independence. We tend to think that, okay, one event is not influencing the other, then it is going to be independent. And that's true, okay? But according to this mathematical definition, even though two events may seem that they will have interaction, they can still be statistically independent. And we can create examples like that. So to start with, let me show you the definition again, in case you have forgotten that. So this is lecture 2.5, and we have gone through some of these materials. This is the definition of independence. We say that two events, A and B, are independent if this equality holds. On the left-hand side, you have a probability applied to the intersection of A and B. And on the right-hand side, you have this product of probability A times the probability of B. Okay? And so that is the definition of independence. Now, you can also visualize the concept of independence through the lens of conditional probability. If you look at the conditional probability of A given B, which is the ratio of A intercept B divided by B, then you can see that if A and B are independent, then A given B will just be A. Whether you have this B condition on B or not does not change the probability of getting an A. Okay, so that you can also see it from the concept of conditional probability. Now let's go through a few examples. And some of these examples we have already discussed last time, but it doesn't matter to just go through them again. Example 1, you throw a dice twice. And the first dice is 3, the second dice is 4. And clearly, the second event doesn't interact with the first event. Intuitively, they are independent. And indeed, it is the case because the probability of getting A and B will be the probability of getting this pair of numbers, 3 and 4, out of 36 combinations, right? And this is 1 over 36. We can also calculate the probability of A, which is 1 over 6. The probability of B is 1 over 6. And so the probability of A times the probability of B is 1 over 36. And these are equal. And so we say that they are independent. A and B are independent because the probability of A intersecting with B is the same as the probability of A times the probability of B. Okay? Very simple definition, and it's intuitive. Now let's look at this example. This is a little bit more trickier. When you look at these two events, one event is actually having an interaction with the other event. The first event is that your first die is 1. Event B is that the sum is 7. And clearly, if I know that the sum is 7, that is going to interact with the first event, because if I got a 2, if I got a 1, it's going to have some interaction, or vice versa, right? If I know that my first die is 1, then the chance of getting a 7, the sum is 7, there should be some interaction. And we tend to think that there will be dependence. Okay? And now let's look at this definition, and then we can go back to the intuition again. So the probability of A is, of course, 1/6. And the probability of B is, that's a little bit more interesting. Sum equals to 7. But among these 36 combinations, how many of those can give you sum equals to 7? 6 of those. It will be 1/6, 2/5, 3/4, 4/3, 5/2, and 6/1. You guys following me? Okay, so you can just count all these cases. So that would be 1/6. You have 6 cases out of 36 combinations, so you have 1/6. Okay. Now, if you're not following, let me just write down. This is 1/6, 2/5, 3/4, 4/3, 5/2, and 6/1. Okay, 6 combinations out of 36 possible combinations. So this is 1/6. The probability of A intersect B. This is what? Now you got to fall into this category. Sum has to be 7, and then the first one has to be 1. Okay, so how many configurations among the 36 possible outcomes can you give this intersection? 1, which is 1/6. Okay, so this is the probability of getting 1/6, and this is 1/36. And clearly you can see that this intersection is the same as the product of the two. And so they are independent. They're independent. How can this be possible, right? So one event is interacting with the other event. Yes? Not quite. So let's think about the other perspective, okay? I give you this first dice equals to 1. The second one is sum equals to 7. Let's change the numbers. Let's change the numbers. How about we change this first dice equals to 2, or first dice equals to 3 or 4? Will this conclusion be changed? No. Okay, it will still be the same. How about we change sum is 6 or sum is 8? Will that change the conclusion? Think about that. If I change sum is 7 to sum is 8 or sum is 9, will it change the conclusion? Some are nodding your head, right? So let's do some quick calculation to prove that. Okay. So here's example 2b. Sum is 8, and this is still 1. And we agree that even if I change this to 2, it doesn't change anything, right? So let's just look at event B. Sum is 8 now. What is the probability of getting B? We can count the cases. To get an 8, you have 2 dice. It has to be 2, 6, 3, 5, 5, 3, 4 and 4, 6, 2. So there are 5 possible combinations that can give you this sum equals to 8. So what is the probability getting B? Your 36 possible outcomes. 5/36. Okay. And probability of A is 1/6. Okay. And probability of getting A and B, 0. Okay. Probability of getting A and B is 0. There's no way that you can have probability of A intercept B equals to the probability of A times probability of B. Okay, so now let's go back to here. Okay, before I do that, if you don't like this 0, you feel this is just too outlier, make it to 2. Okay, make it to 2, okay? You have a different number. If you make it to 2, then you will have, let's say this is 2, then probability of A is 1/6, probability of B is 5/36, but then the probability of A intercept B will be, how many? You have 2 cases, right? You have these 2 cases. No, okay, you only have 1, so you will have 1/36. Okay, you only have this one is allowed. Okay, so it's not necessarily that you will get 0, okay? Even though you get a non-zero number, you will still run into trouble. Okay, so now let's go back to here. In the previous slide, we have sum equals to 7. Now I change the sum equals to 8. This one is dependent, okay? So this is dependent. And this one is independent, according to the mathematical definition, right? So clearly, this sum, right? This notion of sum is interacting with the first dice. There is an interaction. You clearly see that. Intuitively, we would believe that there will be dependency, but mathematically, there isn't any dependency. Okay? There isn't any dependency. So, and here is the way to think about it. What is conditional probability? Okay, what is conditional probability? So the conditional probability of A given B is what? It's actually probability of A intercept B divided by the probability of B. Okay. And remember this diagram. You have A here, you have B here. This is your A, this is your B. Okay, this is your A and B. And what is this ratio? The ratio is here, this is A intercept B, over your B. And that's a ratio, that's a number. This is a number between the size of these 2 sets. Okay, it's a number. It's a number. It's not an event. It's nothing. It's a number. Okay, so you're collapsing many events, many possible outcomes into a number. Remember that. Okay, it's a number, and the number is a ratio. So what is the probability of A? The probability of A is, of course, just A. Okay, it's just A. Now. Why do we say that 2 events are independent? Well, we say that the 2 events are independent when these 2 are the same. Right? So these 2 are the same. Now, what is A? Well, here is your set of A. And this probability of A is the probability of A divided by the probability of omega. And so what you're looking at is the size of this A relative to the sample space. That is another number, and this number is the ratio of the size of these 2 sets. So then when we go back to understanding the conditional probability and independence, what we're asking is that are we able to construct 2 events, A and B, in such a way that this ratio is the same as that ratio? If I can make that happen, then this A and B, they are independent according to the definition here. Okay? Doesn't mean that A has no influence of B or whatever. Okay? It's more about whether your ratio, this ratio, is preserved. Okay? In the 2 cases. So if you have these 2 at the same, then this size divided by the sample space is the same as this divided by B. So let's say this circle occupies 20% of the entire sample space, right? So that will give you 0.2. If this little area occupies 20% of B, then you say that these 2 events, they are independent. That's the way to think about independence. It's not just intuitively, one event is not interacting with the other because that's going to cause problems. Okay? The definition of independence comes from this ratio, this perspective of ratio. Okay? Question? Right. So I'm saying A and B are independent because for A and B to be independent, I need probability of A intercept B equals to probability of A times the probability of B. This is the same as I'm saying that probability of A given B equals to the probability of A. These two are equivalent, assuming that both sets they are non-empty. Right? And the argument is that this A given B can be written as the ratio of A intercept B divided by B. Right? And so if this is the same, then that will also hold. So I'm saying that this A and B are independent if this statement is true. Okay, so yeah. And the way to look at it is to look at this ratio, the ratio between the sets. Just to avoid falling into any cracks. So if you apply your intuition, most of the time, we'll say 90% of the time you're right. But I can create caveats to make it fail. Okay, so don't completely fully rely on your intuition here. If you want to apply your intuition, think about this diagram. So that would be more accurate. Does it work? Okay, any question? Okay, so now let's look at more examples. So this is 2b, and let's look at 3. I thought this is the same. Okay, this is the same. Okay, so now let's look at, that's just explanation. So let's look at example number 4. So in this example, we have max equals to 2, mean equals to 2. Actually, we have gone through some of these logic before, but let's just quickly show that whether this A and B, they are independent. So you have this dice max equals to 2, so probability of A will be, let's see, what other cases that can give you max equals to 2? So that has to be 1, 2, 2, 1, and 2, 2. So that the max of these two numbers will be 2. If you have 3, 2, then the max will be 3. Is it okay? So this is the event of max equals to 2. So I have 3 over 36 for A. The mean equals to 2. How many cases are there? Let's see. You have 2, 2 will be okay. Right? 2, 2 would be okay. What else will work? 2, 3. Okay, 2, 3, the mean is 2. 2, 4 will work. 2, 5 will work. And 2, 6 will work. Okay. What else? Mirror, flip it over. Okay. So you have 3, 2, 4, 2, 5, 2, and 6, 2. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So probability of B, you have 9 over 36. The probability of A intercept B will be, what would be the intersection? 2, 2, okay. So that would be the intersection of the two events. So this is going to be 1 over 36. If you multiply A and B, will you give this intersection? No. So you say that probability of A intercept B doesn't equal to the probability of A times the probability of B, and so they're dependent. So you can create all these examples by changing, okay, what if you have a 4-face dice, then you have max equals to 2, mean equals to 2, you can do similar calculations. And you can also create examples to make it independent. Okay. it depends on how you set up the sample space, how you set up events A and B, you can make it into independent. So I hope this sequence of exercises have shown you some ideas of how to deal with this concept of independence. Now, why do we care about independence? Here is a sort of high-level illustration. It's very vague to you at this point. As you are moving on to do machine learning, big data, you're going to deal with a lot of data points, many samples, many images. In these situations, of course, these data, they will have dependency. Right? But then as you're developing algorithms, as you are trying to prove something, if you want to take care of every bit of dependence, life would be so bad that you can't really derive anything, and you can't really implement anything. And so in many situations, engineers, we're lazy guys, and if the problem allows, we'll always assume some level of independence. Why? Because if all these samples are independent, then this intersection of probabilistic events, you can just look at individual events and then take the product. That's a lot easier, right? So you think about, would it be easier to take a 25th dimensional integral versus you take a one-dimensional integral and take the power to 25? Of course, the latter is a lot easier, right? So similar things will happen in machine learning and data science, where you just simply don't want to deal with all these dimensionalities all at once. You want to chop them into individual dimensions and say that, hey, yeah, even though there's some level of dependence, let's ignore that, and let's derive something. That will usually help you save a lot of time. And in many cases, even though the independence assumptions, they are not fully satisfied in practice, I would say in many cases the algorithm will still work. You can still get some meaningful numbers, and life is still good, right? So assuming some independence will help you do a lot of things. Okay? In this diagram is that you have a lot of molecules. If you want to track everyone, okay, you want to track everyone, it's going to be a nightmare. And you say that there are correlations between molecules and molecules. Unless they're totally correlated, then you just look at one, right? But if there's some level of correlation, and so you want to deal with the correlation between individual molecules, that's not easy. But if you assume that all the molecules, they are just randomly moving around, then you can just look at the statistical property. What is the average? That would be it to describe the event. And so this notion we will come back and visit again as we are going to talk about the limit theorems. Central limit theorems and law of large numbers is all based on this notion of independence. Okay, so just keep in mind that why independence is useful is because when you deal with large-scale systems, you will need this notion of independence to help you really solve a problem. Okay? All right, so now let's move on. Okay. So before I talk about Bayes' theorem, I actually find a very interesting problem as I was preparing this lecture. This is a book problem from this book. It's a very good capture of what we have learned so far. It's a realistic problem, with the only caveat that this medical school, this name is changed. Okay. All right, it's actually a real story according to the authors. All right, so what is this problem and why am I explaining it here? The problem states as follows. There is an automatic breathing apparatus B. Okay, that's a real problem. That's a breathing apparatus that will fail with probability of PB. Okay, it's not that great, right? It has gone through FDA or whatever, but it has some failure probability. Let's say it is PB. Now, a failure means death to the patient unless a monitor system M detects failure and alerts the physician. Okay, so now there are two parties in this game. There's an apparatus, B, and that has certain probability of failure. And then there's a monitoring system. When will the patient die, according to the statement here? Yes. Yes, if the apparatus fail and your monitor system is not alerting the physician. So both B fail and M fail. Okay, then the patient will die, according to this scenario. Okay, all right. So the monitor system fails with probability PM. The failure of the system are independent events. So these are just two completely different systems. One fail will not affect the other failure. Okay, so just to make it clear. All right, and then there is a Professor X, not me, okay, because I'm not an MD, at this medical school. Fortunately, I'm not in a medical school. Argues that if the probability of this monitor system fail is bigger than the probability that the apparatus fail, then installing the monitor system is useless. Now that does have some kind of rationale, right? So if your apparatus fails at certain probability, let's say here is 5%, and if your monitor system doesn't detect that 5%, if your monitor system fails at an even higher rate, let's say here it will be 10%, then you're not going to catch the failure of your apparatus. Then you shouldn't use it. Okay? Then this monitoring system is useless. And so his argument was that let's just look at this probability PM and look at the probability of PB. If PM is bigger than PB, it's useless. Okay? All right. And then the authors is pretty interesting. He asked us to show that this Professor X needs to take a course on probability theory by computing the probability of patient dying with and without the monitor system, assuming that PM equals to 0.1 and PB equals to 0.05. All right, so that is the question. Now, of course, we cannot write a letter to this Professor X and ask him to retake the course, but let us discuss how can we answer this question. Now, I promise that we have all the tools already. We have all the tools. Okay, we have independence. We have conditional probability. We don't even need more. We have all the tools here. How can we answer this question? Now, that's a realistic question. Yes.
We could see PM given B, and like that's when the patient dies.
PM given B. So one suggestion is look at probability.
Yeah.
M given B. So let's write it out. So this is the probability that monitor fail given that the apparatus fail. Okay, is it this one you're looking at? Yes, okay. So let's hear another opinion.
So we can compare two cases where the monitor fails given that apparatus fails, and one is basically probability of apparatus fail given that the monitor fails.
Okay, so one is app fail given that the monitor fail, right? Okay, what is the other one? The other one is this one, right? Okay, so your suggestion is that let's look at these two. Let's look at these two. Okay, how about other people? Yes. probability of mon fail. You say intersection?
Yeah.
App fail. Okay, so that's a third opinion. What else? Anyone else? Yes, please. Mhm. Okay, so we're getting closer. Okay, so we should look at the probability of patient die. Okay, condition on a use monitor. That's actually the question that he asked. Okay, and then we should look at the probability the patient die when not use monitor. This is actually the question that he's asking. Okay. So now of course we have these numbers. We haven't calculated them yet, but clearly these are the two probabilities that we should calculate, right? And now let's say in 5 minutes later we have calculated these two probabilities. It will be some number. It will be some number. What kind of conclusion can you draw based on the magnitude of these two numbers? Now, one has to be bigger than the other. What kind of conclusion can you draw? Let's say this is bigger than that, or this is bigger than that. What kind of conclusion can you draw? We know that after we do all the hard work, we will come up with a number. Yes?
If the monitor is useful at all?
Yeah, whether the monitor system is useful. So if I use the monitor, and then the probability of dying is higher than not using the monitor, then the monitor system is useless, right? And so we got to show that this is the direction. We want to show that. Now, if we can show that, then we're done, right? The conclusion will be valid. Okay, so now how do we calculate these two probabilities? How do we calculate these two probabilities? And many of you have given me these conditional probability intersections and so on. But then the actual question is asking about these two. How do we go from here to here? Yes? Okay, so we are getting there. Okay, independence. This word of independence coming out. Independence coming out. And the independence can be applied to here, okay? Because the monitor system and the aberrators, they are independent according to the statement of the problem. They're independent. And so what will happen to this intersection? Two products, right? It will just be the product of monitor fail times the probability of app fail. It just be that, okay? How about these two conditional probabilities? Yes. Okay, see that? Because they're independent, this conditional probability has nothing to do with it. Okay, it's just the probability of monitor fail. This is just the probability of app fail. Right? I think we're getting closer and closer. Right. Okay, so now let's go back to here. Let's just connect the dots. We have all the tools ready. Let's connect the dots. The probability that a patient die, given that he or she uses the monitor system, there's only one reason that the patient is going to die if he's using the monitor system, which is that the monitor fail and the apparatus fail. This is the same as this one. Okay? Although mathematically, symbolically, we can't draw any connection. But if you think about it, this event is the same as that event. right? If you're using the monitor system, and if the monitor system, now if you're using the monitor system, there are only two possible cases of the monitor system. Either it works, or it doesn't work. There's no third case, okay? So if it works, then it should be okay, okay? Because if the monitor system works, even if the apparatus fail, you will alert the physician, so the life will be saved. So it got to be that the monitor system fail, and the apparatus fail. Then the patient will pass away. Okay, so these two are actually the same event. And so now you calculate what is the probability. Well, you have this already calculated, right? And so that will give you monitor fail, this is 0.1, and then apparatus fail, this is 0.05, so you have 0.005. And this is the probability that the patient die if he or she uses the monitor. Good. How about the other case? The patient die not using the monitor. Actually, we have already heard the answer. It would be what? Yes? 0.05. It would just be 0.05, because this is actually the probability that your apparatus fail. That's it. Because you're not using the monitor system, it's equivalent to that your monitor system always fail. Right? So this is 0.05. So now you compare this probability and that probability. One is 0.005. So this is 0.005. This is 0.05. And which one is higher? Clearly, this is 10 times higher. 10 times higher. Okay? All right, so of course, Professor X has to take a class in probability, but let's go back to this example here. What am I trying to show? With all the tools, conditional probability, independence, when we encounter this problem, try to think from the problem's perspective. Try to think from the problem's perspective. Yes, we have all these mathematical tools sitting around we're very familiar with, but to connect to the actual problem, there is a little step, very, very small, very tiny step to go from here, what the question is actually asking, to the tool that you have. And you ask, what is in between? There's nothing in between. You just think through that step is there. Okay? So many of these problems in our class would be similar to this kind of issue. And in fact, in many of your real-life problems that you go to a company, you work in those companies, you will be given problems like that. There won't be a professor setting up a problem nicely, calculated this probability, but it will be like, okay, what's wrong here, right? So then you have to, you need to take the steps to bridge all these little gaps. So I hope this is stimulating you a little bit to motivate you to think about the problem from a different way. Good? All right. Now I'm going to introduce another problem. Are you ready? Okay. So this is lecture 2.6 on Bayes Theorem and Law of Total Probability. And let us start with this extremely interesting three prisoners problem. Okay. So there are three prisoners, unfortunate three prisoners. Let's draw their face, okay. Okay, are they happy? No. Okay, three prisoners, okay. A and B and C. Part of my drawing, okay? Okay, so you were A, you. Okay, sorry, okay. the king is not me, okay? So there's a king. The king is always happy, right? Okay, so the king decides to release 2 and remove the other one. Okay, so that's the king. Your chance of release is obviously 2/3, right? It's obviously 2/3. Because there are 3 people, and you're one of those, and the king has decided to release 2. So the chance of you being released is 2/3. Okay, and then you suppose that you know a guard very well. Okay, so there's a guard. Usually the guard is the guard happy or not? Okay. Okay, usually it's like this. Okay, so this is the guard. It's like a farmer. Okay, so this is the guard. Okay, so the guard is here, and then you ask him. Now, you cannot ask him about yourself. That's the rule. Okay? Now, don't challenge me there. This is the problem set up. Okay, you can talk to the guard. The guard can tell you about prisoners B and C. B and C. So the guard will tell you, okay, B will be released. Or the guard will say, C will be released. Now, it got to be one of those because 2 released. Regardless if it is you or not, the guard will tell you B or C. All right. So now you talk to the guard tells you B or C, then you have an extremely bad day. Why? Because originally your probability of being released is 2/3, but after you have spoken to the guard, your probability becomes 1/2. Why? Because if the guard has told you that B is released, then it's only the game between you and C. Yeah, your chance of being released just drop from 66.66% to 50%. So you have extremely bad day and you regret, why should I talk to the guard and make me so unhappy? Where is the issue? Where is the issue? There is a flaw in the logic. Where is the flaw in the logic? Okay, keep this in mind. We'll come back to this question. If not today, then on Monday, we will talk about that. Okay, just think about this question. Okay, how come the probability will go from 66% down to 50%? What's going wrong? All right. So I'm going to skip some of these slides, and then I want to talk about some tools, okay? Some tools to solve this problem. The tools we need, there are 2 sets of tools, mathematical tools we need to solve this problem. One tool is called the Bayes Theorem. This theorem is one of the most useless and most useful theorem at the same time. Why do I call it useless? Because it's just the definition of conditional probability. Why do I call it useful? Because you can flip the order of conditional probability. What does this theorem state? The probability of A given B is written as this ratio of B given A times A divided by B. The right-hand side looks extremely complicated. You have 3 probabilities putting in a ratio that you can never remember. But the proof is only one line. There's actually no logic. It's just definition. The reason is you move the probability of B to the left-hand side, then you will get probability of A given B times the probability of B. This is the left-hand side. And this is going to give you the probability of A intercept B. Now you flip the order of A and B. This is the same as the probability of B intercept A. And this is the same as the probability of B in given A times the probability of A. They're the same. That is the theorem. Okay, how useless is this? It's just a restatement, rearrangement of the definition of conditional probability. And that's called the Bayes theorem. But it is useful because you enter the game with B given A. And then you exit the game with A given B. So if I want to calculate A given B, and if I know B given A, I can actually use this Bayes theorem to flip the order around. Now, if I don't use this Bayes theorem, I'm sort of stuck. But even if you don't have this Bayes theorem, you're still okay. Just apply the definition of conditional probability, go through this logic again. You can get to this point. But the whole point of the Bayes theorem is that it's a tool to allow you to flip the order of A given B and B given A, which is going to be very useful. Okay? And that is actually the proof. Don't ask me, where's the proof? This is the proof. Okay. Now, there is another tool that we're going to learn. It looks extremely complicated, but it's actually very easy. Okay, let me explain what's going on here. This is called the law of total probability. What it says is the following. I have a sample space, and then I have an event called B. How do I calculate the size of B? It could be hard, but what if I can cut my sample space into 3 smaller subsets, A1, A2, and A3. They form a thing called a partition of the sample space because when you take the union, they form the sample space and they are all disjoint, and so we call them the partition. And so here is the picture. And what this theorem says is this. The probability of B, right, probability of B is just probability of B inside A times the probability of B inside A2 and the probability of B inside A3. It is this meaning, okay, on the right-hand side. And so if you are still not quite following, then let me draw this diagram here again. So this one is, this area is the probability of A1 intersect with B. Okay, it is an intersection. It's A1 intersect with B. This one is the probability of A2 intersect B. And this one is the probability of A3 intersect B. A1 intersect B is the probability of B given A1 times the probability of A1. That's just the definition of conditional probability. And here is the probability of B given A2 times the probability of A2. And this is the probability of B given A3 times the probability of A3. And since individual pieces can add up to give you the probability of B, you can just add these things up. And that is the formula on the right-hand side. So what does it mean? It means that if I have a set I want to calculate, and I don't know how to calculate because there are just many possible situations, conditions that under which that certain event will happen, right? So I can decompose my big event B into smaller cases. And if I can calculate all the probability of all these smaller cases, I can just add them up, which is a really useful thing. Okay, so I want to give you assignment today, okay, which is a problem that you can work on it this weekend. It's this tournament problem. You have you're trying to play against 3 types of players, and then you have the chance of winning, okay, 0.3 chance of winning a type A player, and then your probability of winning is 0.3, and half of these players, they are player A. And then 1/4 of the players, they are player B, and you have a higher chance of winning over them. Player C, they are the easy players, then you have 0.5 probability winning over this 1/4 of these players. Okay? So what is the probability of winning the game overall? who knows which player you're going to play with. There's a random probability of getting a player, A or B or C, but what is the probability of actually winning the game? And that's your assignment over this weekend. Try to think about that, and then we'll come back and we'll discuss it. Okay?